Did you know that your Arduino Uno has 13 digital input output pins? That's pretty many. You can interface with a lot of sensors with that many digital I/O pins. You can control a lot of outputs with that many input output pins, but sometimes it's not enough. Well, today we're going to talk about a integrated circuit, an IC called a shift register. And this shift register has 8 output pins, and you can send it a byte from your Arduino, and this byte has 8 bits, and any bit that's 1 will turn on one of the outputs of the shift register. Any bit that's 0 will turn off one of the outputs on the shift register. So this is an example of using a serial interface, basically sending data that's a sequence of bits, zeros and ones, and converting that serial data stream into parallel outputs, controlling multiple things at the same times. So let's do it. Okay, so here's the circuit set up on a breadboard. Right here, this integrated circuit is the shift register. It's got 14 pins. It's a 14-pin DIP chip, dual inline package. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pins, and it's interfaced right now with the 7-segment display. Well, this pin, some of these pins are for power. It's a power device, so I have a connection to 5 volts and ground over here to the breadboard. And 7 of these, 8 of the pins on the shift register are digital input-output pins. And 7 of these 8 pins are interfaced with this 7-segment display to control the 7 segments, LED segments on the display, through these 7 current-limiting resistors. So we did an activity in class where we controlled the 7-segment display using 7 digital input-output pins on the Arduino. When I use the shift register, the only thing I need from my Arduino is 1, 2, 3 digital input-output pins. So the purpose of these 3 connections, one of them is the data line. Another one is called the clock. We'll talk about what that means. And then the other one is, let's call it a latch for right now. And so the way this works is this chip has some memory built into it, 1 byte of memory. You send data to the chip, it stores it in this byte, so that's 8 bits. Each of those bits corresponds to one of the digital input-output pins and tells it whether to be on or off. And it depends whether the bit is a 1 or a 0. You can send new bytes via the data line, and when you want to have the chip pull one of those new bytes into its memory, you do something that's called clocking it in using the clock pin. We'll talk about how that works. And then when you are finished sending data to the chip and you want it to be displayed on the output, you set the latch pin high, and that data goes to the output. So instead of needing 7 digital input-output pins to control the 7-segment display, now we only need 3. 1, 2, 3. And we could actually daisy chain a bunch of these shift registers together to get 8, 16, 32, 64 digital input outputs. And we can control all of those outputs using just 3 pins on the Arduino. All right, so we're going to send a serial signal, a sequence of bits from the Arduino to the shift register, and then that serial input becomes parallel output across many different channels, many different input-output pins. All right, so let's take a look at the code that makes this work. All right, so here's the sketch that is producing this 8 on the 7-segment display using the shift register. Let's take a look at it and see if we can make sense of what's going on here. So there's some new elements in here. One thing I'm doing here is I'm defining some variables of type int at the top here. And these are going to be the digital input-output pins on the Arduino that I'm using. I'm going to use pin 7 to send data. pin 6 to send data, pin 7 is going to be my clock pin, pin 8 is going to be my latch pin. And since these numbers aren't going to change anywhere in the code, I'm using this modifier here, CONST, which stands for constant, because those values are not going to change. Those variables are going to be constant throughout the entire sketch. They're never going to change. And so I do this, it takes up less space and memory to make a variable a constant instead of something that can actually change. All right, then I have a variable type byte that contains the data, 8 bytes, 8 bits that I'm going to send to my shift register 1 bit at a time. And so 7 of these are going to be telling input outputs on the shift register to be on, and 1 of these is the input output is off to turn on all 7 segments of the 7-segment display. All right, so let's take a look at the setup. I'm just setting these 3 digital input output pins, 6, 7, and 8 as outputs on my Arduino so they can source current. And I am writing the clock pin low. All right, the clock pin is low to start out. All right, let's take a look at the loop. So in the loop, what I'm doing is I'm setting the latch pin low, and I have a comment here. It says when the latch pin is low, set this low to prevent changes from updating the output register. So again, when I want to send new data to my shift register, I want to do that, but then I want that data to reflect the outputs of the shift register, but I don't want it to be relayed to the outputs right away. So when I set the latch pin low, I can change the content of the shift register. I can send it new bits without changing the output. And then when I set the latch pin high again, the new content of the shift register will be displayed on the outputs. And in this case, displayed on the 7-segment display. And then I have a function here called myShiftOut. And this is a function and I don't think we've seen this before, but this function is taking 3 arguments. One argument is the data I want to send, another argument is the number of the clock pin, and then the third argument is the data pin. All right, and then I set the latch pin high and then wait a second before repeating the loop. So let's take a look at this myShiftOut function. All right, this function doesn't return anything, so it's prefaced with void here, but it actually takes arguments. So there's 3 arguments in the parentheses here next to the name of the function. And when you do this, when you declare a function in C++, the function takes arguments. You got to say in the function what kind of data types these arguments are. So here I'm defining these as of data type byte, int, and int. All right, I have a lengthy comment here. It says, the 595 shift register stores incoming bits as the least significant bit in the storage register. The most significant bit gets pushed out. It just falls off the end. More than one can be daisy chained together. When more than one are used in series, they all share a clock and a latch with the microcontroller. The basic operation here is on the rising edge of the clock, whatever is on the data pin gets stored in the storage register. Setting the latch pin high puts whatever's in the storage register in the output register. Let's look at each step here. So I have a variable that I'm defining pin state, and that's going to either be, it's a Boolean, so it's either going to be high or low. I start out by setting my clock pin low and my data pin low to get everything started. And then what I'm doing here is I'm using a shift register, or I'm using a bit mask, and I'm scrolling through, I'm parsing this data byte that I want to send to the shift register 1 bit at a time, and if a bit is 1, then pin state gets set high. If a bit is 0, then pin state gets set low. So I'm going to go through that one bit at a time, and then so pin state will be high or low depending on whether a bit is 0 or 1 or 0. And then I'm going to do a digital write on the data pin to set the data pin high or low, and then I'm going to do my clock pin high and then low. So I set the clock pin high and then low. This is clocking in the bit that is sitting at the data pin, and that gets stored on the shift register. I think some drawings will make how the shift register is working a little bit more clear. All right, so the shift register has, I said earlier, it has 1 byte of memory, but really it actually has 2 bytes of memory. It has 2 registers on it that are each 8 bits, 1 byte. One is called let's call one the shift register, the output register, and the other one the shift register, okay? Let me draw a picture. So we can conceptualize these 2 memory locations as a bunch of boxes, 8 boxes for the 8 bits of the output register and 8 boxes for the 8 bits of the shift register, and they're connected to one another. So data in the shift register can be transferred to the output register. Okay, so let's say, when does this happen? Let's say we have just a bunch of 1s in the shift register. And when we set the latch pin high, when the latch pin gets set high, then whatever in the shift register gets transferred to the output register. So all of these, and remember, each of these bits in the output register control one of the input-output pins on the shift register. So if they're all 1, all the outputs will be turned on. Okay? So if the latch pin is set low, then that disconnects this connection between the shift register and the output register. So we can make changes to the shift register without those changes being reflected on the output register. Until we set the latch pin high again, then all the elements of the shift register will be transferred to the output register at that time. Okay, so that's how the latch pin works. All right, so now let's focus on the shift register and how you get new data into the shift register. Once it's there, we know the latch pin setting it high sends that data to the output. But how do we get the new data into the shift register? Let's focus on that. So let me start by labeling the bit over here as the least significant bit and the bit over here as the most significant bit. And so when new data comes into the shift register, it's going to come into the least significant bit, and then all the bits are going to shift 1 place to the left toward the most significant bit. So if I were to send a 0 into the shift register, that's going to make the shift register change. So the 1 over here at the most significant bit will drop off, and then all the other bits will shift over 1 place. So we'd have something like the 0 would come in here, and then all the 1s would shift 1 place to the left, and we get something like that. So if I send a 1 to the shift register, that's what I get. So I can send a bunch of bits, 1 bit at a time, to update the shift register, and I can update all bits in the shift register by sending 8 individual bits 1 at a time. Okay, so how exactly is that done? Let me show you. So let's say I want to send the byte 01110110 to the shift register. That's what I want. I want the shift register to be 01110110. All right, so the way I would do this is I would begin by setting the, I'm going to send the most significant bit first, because remember, every time I send a bit into the shift register, everything that's in there already is going to shift toward the right. So I'll send the most significant bit first, and then after I send all the other bits, it will be over here in the most significant bit. All right, so what I want to happen is I want to set these bits in the shift register like that. Okay, so the way I'm going to do this is I'm going to start with the most significant bit, and that's a 0. So I'm going to start by setting the data pin low. Okay, And with the data pin set low, I'm going to take the clock pin and I'm going to set it high. And then I'll set it low again. Okay, so I'm going to clock it with a pulse that looks like that. High, low. So these clock pulses look like this. And every time I get a pulse like this, the clock pin goes high and then low. Whatever value is sitting at the data pin will be clocked into the shift register. All right, so the entire sequence of events will look something like this. So the voltage at my data pin is going to look like this. It's going to be low and then it's going to be high. So I can clock in 3 ones, then it'll be low again, so I can clock in a 0, and then high, so I can clock in 2 ones, and then low again. And with the voltage at the data pin looking like this, I will then operate my clock pin like so. At my clock pin, I'm going to send a sequence of pulses, high and then low, very quickly. And every time the clock pin goes high, from low to high, whatever value, whatever voltage is at the data pin gets shifted into the register. So whatever value we have, let me mark where that will occur. So right here, whatever the voltage is, right there, 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 and right there, those values will be shifted into the shift register. So by clocking the clock pin in this way, where the data pin is set in this way, what I'll accomplish is I'll send a 0 to the shift register, then a 1, then a 1, then a 1, then a 0, then a 1, then a 1, then a 0. Every time a new bit gets sent to the shift register, everything that's in there already gets shifted one place to the left toward the most significant bit. So at the end, that's what's going to be on the shift register. And then when I set the latch high, that will be sent to the output register. And any output pin that has a 1 in the corresponding bit of the output register will be turned on, and any output pin that has a 0 in the corresponding bit of the output register will be turned off. All right, so there's a lot of new stuff here, everything from introducing you to the idea that some variables in your sketch can be constants, which means they're not going to change, to this concept of sending data in a serial fashion using a serial signal, and the actual signal takes the form of voltages that are low or high, and then there's a clock signal which determines when the actual data at the data pin is being read into, in this case, the shift register. All right, so that's it for this lesson. See you next time.